So let's think about area calculations for a second and go back to first principles. So if we're looking for distance traveled, it seems to be the area underneath the graph of velocity, even when the velocity is changing. All right. Now let's take a more general step back and say, let's not worry about velocities. Let's just ask about area calculations in general. And it's pretty easy in some cases to do that. Let's take a look at this graph here. Y equals x plus 1. There we go. 1 intercept, slope 1. From x equals minus 1 to x equals plus 1. Well, if we range that out here, we get a triangle. That's the area we're looking at there. And if that's the case, well, we know that area. That area is 1/2 base times height. And that would be 1/2, the base is 2, from my -1 to 1. The height at the very peak there is also 2. That's another 2. That area is then 2 overall. Oops. Okay, that was easy. This is going to be a cinch. All right. What other kind of areas might we calculate? The area between the x-axis and the graph of y equals the square root of 1 minus x squared. Now that's a little trickier, but if we rewrite that for a second, y equals square root of 1 minus x squared, and let's square both sides. If we do that, we get y squared is 1 minus x squared, and let's just bring that over to the other side. X squared plus y squared equals 1. That is the formula or the equation for a circle. And so the part of this graph that we're talking about here is the top half of a circle. And then we know the area. Top half of a circle will be, well, the area of an entire circle is pi r squared, and we just want half of that. So there's our whole circle. And top half. All right, and the radius here is 1. Whoops. Our radius here is 1. So in this particular case, we get 1/2 times pi times 1 squared, or pi over 2 square units. All right, so easy, fantastic. We know how to find the area underneath a circle. Now here's the humbling part. Try to think of all the shapes that you know right this second for which you can calculate the exact area. We're talking just square areas here, so not three-dimensional volumes, just areas. I think most of you quite happily will say triangles, circles, or parts of each of those. Rectangles, obviously. What else might you have? Parallelograms. Trapezoids, you might have that, because they're all made of, well, wait, hold on, yeah. These are all made, except for circles, these things are all just made out of triangles, or triangles and rectangles recombined. Trapezoids you can think of as a rectangle with triangles added or taken away. Parallelograms, same thing. Really, we only know how to find the area from high school math of a very, very limited set of shapes. If we look back at our earlier example that we had there, oops, sorry, just going back here. There we are. Go back to our quick sketch of the area we'd like to find underneath, say, a velocity graph. That's not something we've got in our toolkit for the most part, unless you've seen calculus already. So just be aware of that. We've got a big step that we need to take here in terms of understanding how we can calculate the area under graph. This is a hard problem. This is something that, except in very special cases, is actually very, very tricky and took a long time to develop. You're talking origins in the Greeks back in 500, 1000 BC, trying to work up to the time of Newton and Leibniz with calculus.